So Tchetgen, is that Tchetgen? Okay. Sorry for that. So we are incredibly happy to have Professor Eric Tchetgen, who is a university professor in UPenn, affiliated with the Department of Biostatistics, which is in the School of Medicine, and also the Department of Statistics and Data Science, which is in the School of Business. So he has Professor Eric's main research area is causal inference, and recently he has been very active in using causal inference for HIV research, epidemiology, and he has numerous awards. I saw that in most recently he is the recipient of newly instituted Rossiu Award in 2022. So we are very proud to have you here. You can take the floor.
Thank you so much for that introduction, and thank you for having me here today. I get to experience some nice weather. It's a good company. The next 2 days are probably going to be more statistical than the usual talks or tutorials, but I wanted to discuss some issues that as statisticians we care a lot about and we think are relevant to folks who care about learning in general. So I hope that this will somewhat resonate. The techniques actually come from.
So there are few people in Zoom, 12 people to be specific, and they said that they cannot. Where
is the mic?
Mic is so that one, right?
Okay.
Yes,
can you hear me better?
Dimitri?
Oh,
yeah.
yes.
Okay.
Okay.
Yes, thank you.
Okay. I'll stand over here. All right. So I'm going to talk about the Forster-Warmuth, what we call non-parametric counterfactual regression. So this is a technique for learning regression models non-parametrically, and which we found to have some really appealing properties. So I'm going to try to make the case for that. And we applied them to a context of what we name counterfactual regressions. These are regression models where the outcome may not always be observed. So these are things that you care about if you have missing outcome. Imagine you have like a covariate shift problem and the data set where you don't see the outcome and want to predict it. Or you have a causal inference problem where you want to infer what would have happened to someone who was treated had they not been treated. So these are counter to fact what would have happened to the outcome. So we care a lot about these types of problems. I'm going to try to motivate some of the questions. So the talk is going to be both theoretical and also applied, but the motivation is really applied, and we want to have methods that have well-established theoretical guarantees. So that's sort of the goal for today. And then, so just an advertisement for tomorrow. Today I'm going to focus about regression. Tomorrow is going to be more closer to conformal prediction and techniques for conformal prediction in context where you have a time to event outcome, like time to death, or time to progressing with cancer, or time to a heart attack. And the issue there is that the outcome is not always observed because people drop out. They're censored either because the study ends before they experience the event, or they are lost to follow up. Okay? So it's very different from the standard conformal prediction setting. And so that's going to be the talk for tomorrow. Today is again going to be a regression problem where the goal is not to predict the outcome, but rather to learn about the association between the outcome and some covariates, and have a guarantee to learn about that relationship. And so this is the outline of my talk. I'm going to start with just a brief review of non-parametric series regression in statistics. So I'm sure it's going to be much review, but it's going to establish those aspects of that literature that I'm going to care about today. Okay, and then I'll describe the Forster-Warmuth non-parametric series regression. So this is an adaptation of a technique that was established by Forster and Warmuth in a paper of theirs, where they were interested in agnostic online learning and providing some guarantees there. And we're going to adapt that framework to a setting where we're actually interested in agnostic non-parametric regression learning and show that their methods actually have some really nice generalization to that context. And please jump in if you have any questions at any point in time. This is quite, we're in California, so this is supposed to be laid back, right? And then we'll switch gears a little bit. I'll introduce this concept of non-parametric regression, counterfactual regression, and Forster-Warmuth version of that. Give some explications and present very briefly some simulation studies to show that these actually theory translate to practice. So some of these good properties actually can be seen reflected in data, and some concluding remarks. All right, so regression analysis plays a central role in statistics, more broadly in scientific inquiry, where one may seek to learn about a conditional mean regression as a function of covariate X. Yeah? And ideally we want to learn this without putting a priori restriction, like assuming that the relationship is linear or follows a parametric family of models. We would like to almost only assume that the relationship might be smooth. And we'll codify that more precisely. But beyond that, not really impose additional structure. We want the data to speak, but we don't want it to overfit. We want the data to speak up to a point where we can actually control the amount of fitting. Okay. So here's some example. Beyond just a regression function, you might be interested in the conditional cumulative distribution function. So the proportion of individuals who have an outcome below a certain threshold T, conditional on the covariates, and that also leads to estimation of conditional quantiles. And more broadly, you might have a loss function role, and you're interested in a non-parametric function data that solves, that minimizes the expected value of the loss function. So imagine that data was actually the regression curve, then this loss function could be the quadratic loss. And that would just be mean squared error minimization, and you would be back at the regression formulation. So this is more general because depending on the loss function, you recover, may recover. Let me just sign it. A different kind of regression curve, including instrumental variable techniques, proximal causal inference, things that I will mention in passing throughout today. So just to keep in mind that we're not only restricting ourselves to regression models, but far more general kind of objects that might be just a minimizer of the loss function. All right, so just as a brief review, series or sieve estimation approximates a known conditional mean function by taking a linear combination of k basis functions. So imagine I have a basis function. I'm going to use phi bar k to denote the vector of basis function at little x. So if you want to grant ideas, think of these as like polynomial bases. This would be the intercept, so this would be 1, then the next one would be x, the next one would be x squared, x cubed, and likewise you can think of splines, you can think of wavelets, you can think of an RKHS space that's spanned by a particular canonical vector basis system. So a lot of the regression models that we fit use these types of formulation, and then you just use a linear combination of those basis functions. And what makes it non-parametric is you allow k, the number of basis functions, to grow with sample size. Otherwise, it would be a parametric model. So that's the distinction. Parametric model, you fix k, and it's not allowed to grow with sample size. Non-parametric models, you allow it to become more and more flexible. The more data you have, the better the fit. And the idea is that in general, you should be able to approximate any smooth function arbitrarily well. How well will depend on how smooth that function is. And we'll formalize this in a couple of slides. Okay. The way we do this in practice is for optimal performance of our linear combination, you should select which basis function to include and how many to include to balance bias and variance to minimize the mean squared error or any other loss function you want. I'm going to work with bias, square bias and variance, and more broadly with mean squared error. And we to balance it so that we can get the best possible rate for choosing kn. The k little n now makes explicit the fact that the number of basis functions is indexed by the sample size of the data you have. Okay. All right, so now we have this idea that we're going to use these linear combination of basis functions to estimate an arbitrary function of x. The question is, how do we actually estimate the coefficients of that function? Well, one of the oldest and most straightforward empirical approach to construct a series estimator is by least squares. You just run a linear regression, minimize the least squares loss, minimize the square loss. In this vein, I'm only going to deal with IID data today. We have extended this to dependent data, time series data, other kind of forms of dependence, and much of the results actually extend to that setting. So it's quite general and flexible of a framework.
Is the the basis function, is that going to be fixed, or can you choose? Like, suppose you have some data, are you going to also choose the basis function, or are you going to?
That's a great question. So for the time being, imagine I'm doing this for one basis system, wavelets. And for now, I'm going to say you take that basis function, and then we want to select the optimal number of basis function to fit by least squares or the Forster-Warmuth linear. The next question would be, and we want to do this to get the best possible rate of estimation.
Right.
But of course, the best possible rate of estimation, as you'll see in a couple of slides, will depend on how smooth the function is, which is of course unknown. So ideally, you'll want to adapt. In addition to adapting to the smoother function, you may also want to adapt to use multiple basis systems. You want a dictionary of different basis systems. So what we'll show is the property of this basis system will allow you to do so by cross-validation, and you get an oracle guarantee. That in fact, if there is one that an oracle will be able to choose, with some approximation error, you would find that with high probability. But for most of the talk, I'm going to fix it at one basis system. And I'll point out where we have this property that would allow you to do the more general case. Any other question? Okay. So we are going to assume we have an ID data, sample size n. We aim to estimate, and I'm going to use this notation throughout. There's an underlying true function, m star of x. And by the underlying true function, I mean this is a function of the underlying true data generating mechanism, the conditional mean of y given x. So I'm assuming that exists, it's well defined. Okay? And I think that's a very reasonable assumption if you have ID data. All right, and that's going to be our target of inference. And we want to estimate it using, and I'm first going to start by using a standard least square series estimator. That means that, and I want to get a prediction of m star at little x. So m hat of x will be my estimator. Okay, so the hat denotes that the beta is learned from the data, and you get a linear combination. I should use the mouse, I guess. You get a link. This is not going to work. People online can't see when I'm pointing. You get a linear combination of the basis system, and the least squares estimator is the one that's given here for beta hat, where I've now used matrix notation for phi k, which is the n by k matrix of the basis system. So the vectors phi k x1 is a vector of all basis function evaluated at x1, so and so on and so forth, all the way to xn. Does that make sense? The standard least squares regression. Nothing fancy here. I'm assuming the inverse exists. If it doesn't exist, or if it's not unique, use generalized inverse. Doesn't matter. We care about prediction, not beta itself. We care about beta hat combined with phi k x. So far, this looks like a parametric least squares stat 101 kind of regression model. It's a very natural thing to do. The main difference, what makes this non-parametric, is we allow k to grow with sample size. That's not stat 101. Stat 101, k is bounded. Okay? It turns out that that actually complicates the analysis of this estimator. We want to understand how does this estimator behave. And there's quite a bit of theory on understanding how the least squares series estimator behave in a non-parametric context. Several papers provide sufficient conditions for things like consistency. You want the estimator to converge to the underlying mean m star of x in probability. You want the mean squared error to go to 0 asymptotically for any m star of x in a certain functional class. I'm going to work with Holder balls, but you could pick whatever, based off Sybil F, whatever people like to work with, or You can choose that, but I'm going to work with simplest possible one to communicate is Holder balls. I'll describe them in a second. Okay, so people have established quite a bit of theory for this: consistency, convergence rate, how fast do they converge to the truth. In some cases, actually, even that they are asymptotically normal, so you can make inferences, you can construct confidence bands. Here are some papers. Yachong Chen, an economist, is trailblazer in this area. Whitney New at MIT also did some really nice early work in this. Yorfi, Wang, and so on. And a number of econometricians have studied the theory of these squares in non-parametric settings. All right. Yeah.
Sorry, I think I get a little confused between say parametric and non-parametric here. Not a statistician.
That's okay.
So then like even in parametric, like if it were a parametric linear regression, you would have statistical rate where the number of samples. Like, that's function of time, like, n equals to p over like something, or epsilon equals to p over n. And you want to,
so what's different?
Yeah, what is different?
All right, very good. Maybe give me 1 second, I'm gonna say it here. So parametric models, you're right. So the first thing about parametric models is that people assume that the mean of y given x can in fact in the population be represented as a given finite linear combination of basis function. The simplest one is the intercept plus beta x, standard linear model. And then if that's true, then you actually will be unbiased for beta, and then you will be consistent. The variance will go down at the rate 1 over n. Okay. The first thing to note here is if I allow the number of basis functions to go to infinity, then the variance will go at the rate capital K over n. Capital K being the number of basis function. Right. You got 1 over n because you had a bounded number of basis function. Okay. But that actually needs to be proved that you get consistency. For that, you'll need to learn about the behavior of this inverse matrix. So this is a random matrix, phi k, I can't find the mouse. The beta hat, if you look at the definition of beta hat, the first expression displayed, it has this phi transpose phi inverse. That's a random matrix that's growing up as k goes to infinity. So much of these papers is using random matrix theory to control this term. Okay. And there are additional subtleties. Once you go non-parametric, that means there is no linear combination such that there is no bias. You have to, it's only asymptotically that you have no bias. And so the question is, at any given fixed k, there's representation bias. You need to be able to bound that representation bias because you never have unbiasedness. There's no finite linear combination of basis that represents a function because all I'm assuming is that it has a certain smoothness, degree of smoothness. So I hope that gives you a sense of where the complications arise, but it's a big step to go from parametric to non-parametric in this context. And then there's something in between where you say, I'm going to fit a parametric model. I don't care that it's not a correct model. I want to understand these properties. And you can do that. You're going to be biased. You're going to be converging to the best linear predictor. And that could be useful in some settings, like predictions, but often it's not very useful. If you really want to understand what covariates do I need to collect to predict this outcome. And I can speak to some examples a little later. So we're really interested in recovering the underlying function. That's where we anchor our inference. I think there was a question in the chat.
No, I think explained.
Oh, okay. Okay, all right. But that's a very good, all right. Dimitris. Okay, thank you, Dimitris. Yes. Okay. So these prior works, what we've established is that working with Holder space, for instance, so this would be the space of functions that have beta m derivatives. And those derivatives are bounded by Cm, the fixed constant. So imagine imagine I'm only looking at linear functions. Linear functions are analytical, they have infinite number of derivatives, very smooth. Versus imagine I'm interested in Brownian motion. Brownian motion is in this space with beta a half. Beta infinity, analytic function, beta a half Brownian motion. And you could see in your mind a line, very smooth. Brownian motion, very noisy. How do I recover a line? Very easy. How do I recover Brownian motion? Very difficult. So beta indexes how difficult the problem is. The smoothness and the dimension of X together, right? The curse of dimensionality is about the smoothness divided by the dimension. The smaller that ratio, that's the effective smoothness of the function. The smaller the ratio, the harder it is to estimate that function. Okay? All right, so this is a space of functions that we're going to work with. You can ignore CM, it's not going to be that important because I'm going to do things up to rates, not up to constant. Okay, so beta M is what's driving. And just keep in mind, beta M large and very smooth, beta M small, it's very hard. The function is very weak, very hard to estimate. All right, so what they establish is that you can actually, if you look at this L2 error, this is the L2 error comparing the true function M star X to my least squares estimator. And they've studied the L2 error of least squares and showed that least squares attains this convergence rate, n to the minus beta m over 2 beta m plus d. And you can divide by d, the numerator and denominator, and you could see that everything is indexed by beta m over d. So if beta m over d is very small, this is very slow. If beta m over d is very large, this is very fast. In fact, if beta m over d goes to infinity, like an analytical function, this goes to 1 over n. 1 over square root of n, because it's on the standard error. Yeah. That's the parametric rate. Okay, Brownian motion, you'll make beta m over d equals to a half. You get, I can't do this in my head, I shouldn't have, 1 over 2 divided by 1 over 4, 1 over 8. Okay, did I do it right? I think so.
D plus.
D is 1, sorry. Yeah, you're right. So 4, 5. So I said beta m is a half. So you get 1 here plus 1, 2, divided by 2. So you get n2 minus a half. N2 quarter.
1 over 4.
N2 minus a quarter. I shouldn't have done this, but I don't have even slides. Mathematics is very bad. Okay, so you get very slow rates. N2 minus a quarter versus 1 over square root of n. So you can see that anywhere in between, you're assuming some degree of smoothness. 1 over square root of n is what's referred to as parametric rates. Okay? And anything slower than that will typically be referred to as non-parametric rate. And parametric rate, the dimension doesn't matter anymore because it's bounded. And the smoothness doesn't matter anymore because it's effectively treated as infinity. Okay? But we're interested in non-parametric rates because we're not willing to assume parametric models for our functions. And they established that this is the rate of estimation in probability of the error that you would make if you use E squares. The reason I'm going on this is that actually there's some old statistical literature, like it goes back to 1980, where Charles Stone showed that this is actually the L2 minimax rate of convergence. Without any additional assumption, no estimator can go faster than this rate. And note here that I'm assuming that actually that beta m is known. And even if you knew how smooth the function is, you could not get an estimator that was faster than this. So this is fantastic. Why? Because it says you don't have to do anything more fancy than what you know, E squares. You just allow the basis to grow. Yes.
So the minimax bound is proved by constructing a class of functions that are hard to.
Yeah, the least favorable direction, basically.
I see.
So they establish a lower bound, and they show that this is the lower bound, and the lower bound is usually you turn the estimation column the way these proofs are typically done. It's classical lower bound. You turn it into a testing problem, and you want to find that you can bound the likelihood ratio test, which is the most powerful test in this context. If you make the alternative distance 1 over k away from 0. But the likelihood ratio cannot give you a perfect test. And you can translate that into lower bound for the max estimation. So and then you can construct an upper bound. So this is an upper bound that the least squares estimator attains that lower bound. So this is amazing. You don't have to do anything fancy if you know beta m. You just use your least squares estimator. There are a few caveats. The first thing is, this is really nice because it actually applies to a lot of traditional series estimators. Fourier series, wavelets, splines, and so-called local polynomial or partition series. And the economists have studied a lot of these. Okay. The sad thing is that it does not achieve, it's not as general as you might think. It really depends on the basis system you use, because the most natural basis system to use, which is polynomial, 1x, x squared, x cubed, x4, can only be used if the function is sufficiently smooth. So beta m has a value below by d over 2. Okay? And so this restricts the utility of these methods by the basis function, which is not a desirable result, because as you mentioned, you may want to use a dictionary of basis functions. You don't want to commit to a particular basis function. And so I want to say a little bit about this, because actually this is still a motivation for what I really want to talk about today, but it's worthwhile. I want to talk a little bit about how people work on these types of proofs. Okay, so there's a critical role in their proofs about the size of the basis functions. It's a very important part of their proof. And this has to do with how you control that phi transpose inverse matrix. How fast does it converge to a deterministic object? Okay, and at what rate? And it also depends on how smooth the function is. Specifically, the size of a basis function can be measured as follows. So phi k, if you remember, is a vector of basis function. So I want you to think again in terms of polynomials. I stop all the way to capital K, so I have 1 all the way to x to the power k minus 1. That's my vector phi. And this is the Euclidean norm of that. Okay, so I take that vector, transpose, stop it by the vector. So I get the sum, 1 to capital K minus 1, or 1 to capital K, of little x to the power k minus 1. Sum squared, right? It's the Euclidean norm of the vector. And you do this at little x, and then you soup it over all x. That's the size of the basis function. This is how fast the basis function will blow out.
Are we assuming the basis to be orthonormal as well?
No.
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 So we have another
Completely general. What they require for the method of proof is that as the basis function grows, it can, as a function of k, it cannot grow faster than the square root of k, because I'm taking the L2 norm of k objects. Okay, so this is actually quite restrictive, but it actually turns out to hold for many basis functions, like particular basis functions that are compactly supported, like wavelets. But it doesn't hold for polynomials. Polynomials blow up quite fast. In fact, this guy is of order k. So this is why they have a restriction. Polynomial turn out to be universally minimax. If you're going to use least squares, so you probably don't want to use it in practice unless you know your function is actually quite smooth. Okay? So that's the first restriction. And what we're going to do is we're going to get rid of this restriction. We're going to propose an estimator. That's a modification of least squares. That's where the Forster-Warmuth comes into play. That gets rid of this, which means that you are free to use whatever basis system you want, and you'll be guaranteed to be minimax. The basis function needs to have good approximation, and all basis functions I've mentioned today in the slides have good approximation in the following sense. Remember I said we're not assuming a parametric model, which means that if I take any representation of my basis function up to k, and I take an error from the true function, there's going to be a gap. Good approximation error means that gap goes to 0 as k increases. So as k increases, your approximation should get better and better as you use more and more. This is not a statistical problem, this is a representation problem. The function can eventually be perfectly represented, and how fast it can be represented is indexed by the effective smoothness of the function, beta m over d.
This is also a requirement. Both 1 and 2 are requirements.
Both are requirements for least squares to be minimax optimal. This one is a mild, the second one is a mild requirement. Like optimality of neural nets rely on something like this as well. So this is near universal to get a good approximation for virtually any functional space. RHS, any subspace of Hilbert you want, you need this. This one is specific, the first one is specific to least squares. For least squares to be minimax, the basis function cannot be too large. Okay? And so we want to get rid of one, but it's impossible to get rid of two. It's impossible to do better than two. That's a basic requirement for any kind of non-parametric estimator to be near universal approximator. All right, so I think I'm gonna maybe cut my talk in half. I think today I'm just gonna cover the first half, and hopefully that's actually more of the tutorial part. The second half is more the research part. Okay. All right, so that will give me less pressure to rush through the slides, and we can have more of an exchange if we want to. All right, so we're going to look at what's known as a series estimator, a new type of series regression estimator, which is no longer least squares, it's going to be a multiplication of least squares. And essentially, we're going to localize. If I want a prediction at little x, I want the estimator to be minimax at each value of little x. Okay, and to behave well in a way that I'm going to describe. In the sense that it's going to attain the well-established lower bounds for minimax non-parametric rates of estimation in settings where covariates and outcomes are fully observed under weaker conditions than in the previous existing literature. The approach builds on an estimator we refer to as Forster-Warmuth series estimator, which is originated from the online learning literature. And this is obtained via careful modification of the renowned nonlinear Forster-Warmuth forecaster. And I'm going to describe the estimator in the next slide. So just to say, we give a lot of credit to Forster-Warmuth because this is actually their constructions. What they did not realize was that this was useful. They were interested in understanding in an online setting what's the behavior of this particular modification of these squares if you're agnostic as to the regression model. So they're not interested in regressing, in finding out the true regression curve in the y with x. They just want to construct a given linear combination that does a good job in approximating it. Okay. So turning it into a non-parametric setting was not a trivial exercise, but it's the estimator. Turns out the construction is quite general and it's very intuitive, which we really like. All right, so what is their construction? So I have three highlighted terms here, A, B, and C. And these are three modifications we make to these squares. So the first modification is if you set Hn to 0, and you set B to 0, and you set phi kx to 0, you're back to the least squares estimator. Okay? They are both linear combination of the basis system. But they are different linear combination of basis system. So what we do is we're basically localizing the least squares estimator. The least squares estimator doesn't privilege any given value of little x. Right? If I get rid of this term, I get rid of this term, and I get rid of this term, ignoring the basis function, the coefficient doesn't depend on little x, the value of x I'm interested in predicting. It's just a beta hat, just the least squares beta hat. So what we've done is we've localized it by introducing these three modifications to little x. So now let me explain what they do. The first thing I want to point out is Hn of x is defined here. And this is what's known as a leverage core in linear regression. And the leverage course is literally just a measure that lies between 0 and 1. And if you remember your stats 101, leverage is a good thing to detect outliers. What do I mean by that? It detects how far is the x you're interested in predicting from the support of the distribution of the x you observe. If you're very far, that means you're extrapolating. If my data for x is here, and my little x is here, and I want to learn the prediction from data I learned here, I see here, predict what happens here, that's extrapolation. And Hn of x will be 1. And it's going to shrink your prediction to 0. Does that make sense? If the little x is right in the middle of where I have a lot of information, where all the data for x are observed, this leverage score goes to 0. And this is gonna go to 1. And that says trust the regression model. And so we're basically gonna downweight any data that's far away from most of the observed data, if you want a prediction. Why can we do this without introducing bias? Right? If I'm shrinking predictions at little x that are far away from the distribution to 0, I'm certainly introducing bias for n at little x. The reason this is okay to do is because of the loss function we're interested in minimizing, which is the mean squared error. We're going to average over x. And so all the outlying values are going to have very, if any at all, influence on the mean squared error, because they will have mass going to 0. But it turns out that if you don't do that, that behavior in areas where you don't have a lot of data completely destroy the least squares estimator in terms of mean squared error. Okay, so that's the first fix. So what do the other 3 fixes do? So let me talk about B and C. So I talked a little bit about A. B and C incorporate a fake observation. So I'm interested in the value little x. That may not be actually be observed in my data. So it's going to create a fake observation of little x and set the y to 0. So there is a y for that little x at 0. And because I have a value little x, I have to add it to my design matrix. So this is the contribution to this matrix as you observe a value at little x. So that's all it is. And note the transpose here is split because phi kx, it's just the way the matrix are described, are defined. Okay, but everything corresponds. This is for n data point, this is just for 1 data point, just to make sure that they align perfectly. Okay. So little a adjusts for the leverage of this observation. If extreme relative to observed basis functions, this effectively controls the size of the projection matrix and the value of interest little x, regardless of the basis function.
Yes. If we don't have B and C and just have A, would it still be it
would not be enough.
It would not be enough.
It would not be enough. So Ed George, who is a famous Bayesian statistician, when he heard this talk, he immediately said, "This is a." So I got 2 reactions. I have one reaction for Edgar, who is more of a conformal prediction person. He says this is like conformal prediction because you're adding the observation, a fake observation at the value that you care about. And it turns out that this value doesn't have to be 0, it could be anything. The y value you impute can be any value, you pick 0 for convenience. And Ed George's reaction was, this is an empirical based estimator because you're doing something effective like ridge regression. You're localizing it. Ridge regression usually has a general penalty that applies to all x. We're localizing the penalty to little x. That's the intuitive understanding of it. I just think it's a regularization trick. That seems to work quite well. The one thing I want to say, so this paper is under review, and one of the reviewers complained that this is going to be just as expensive as in conformal prediction, where for any new value of x, I have to recompute the matrix. But of course, that's not true because there's very straightforward matrix operations that allow you to compute. Once you have this inverse of this matrix, you can update it by this inverse, and it doesn't scale. It doesn't. It doesn't add to the computational burden at all. So it's actually quite cheap.
What is the burden at each step? Is it
Sorry?
So at each step of the online process, how much burden?
This is not online learning.
Okay.
Yeah, sorry for the confusion. The original Warmuth, Forster-Warmuth, this particular estimator appeared in the online setting. I'm interested in I data. So I give you all the data, and I say I want to get a prediction for m at little x. You could do this in an online setting. Not all our results will translate to the online setting. You will need more conditions. So for instance, we did this for time series, which is very close to the online setting. And we require, you can relax the IID part, but we do require some bound on how dependent the data are. It cannot be perfectly correlated. So I don't know if that anticipates your question or.
So if you really want to do something like this in an online setting, you would do it at every step, you would calculate like your PKs for all previous steps. And then you will compute this estimator at the current X, right?
You could do that, but I can't tell you, I can't give you any guarantees for that because I didn't study that.
Okay.
Does that make sense?
Yeah.
Okay. So, but that's one way you could do. I don't know if it's the best way because I haven't studied that.
So in their original form, okay, so it was not non-parametric, it was, yeah, I see, okay,
Yeah.
so that's
That
what.
is the usual online
It was
setting.
online.
So your guess is as good as mine for that. I don't do online settings. I just like this estimator. Okay. All right, so I have about 15 minutes. So I'm gonna slow down a little bit and then just present a couple of results, but I actually spent some time talking about them. I'm supposed to try to rush out. So what our first result is, suppose that, and we do require this, that the L2 moment, that the second moment of the outcome, condition on X is bounded almost surely. And the basis function phi k satisfies an optimal approximation property such that for each k, there exists a linear combination of my basis function so that I can bound the error, the representation error by k to the minus 2 beta m over d. So that's the approximation error I was talking about earlier, that this is basically a necessary condition to get minimax rate. And it's satisfied fortunately by all the basis functions I've mentioned: Lablet, Fourier, polynomials, splines, neural nets, RKHS. Satisfy this property. Okay. Then it says set the number of basis function to be n to the d over 2 beta m plus d. This is a theoretical exercise because I'm doing theory. I'll discuss how you do this in practice because this requires you to know beta m. I don't know what beta m. I can look at the data that will tell me how this is you can't identify how smooth the function is from the data. But I'll show that you can adapt to how smooth the data is without learning how smooth it is. If that makes sense. That's the usual adaptivity trade-off. Okay. So what we have is that in fact, and there's a big difference here in the sense that I'm actually interested in mean squared error. And I should maybe back up a second because I don't know that I stressed this. The entire previous literature, actually, the result they obtain is in probability. So I'm interested in something, a stronger guarantee, right? A stronger guarantee, mean squared error is a stronger guarantee than just in probability. Okay. So that's what we do here. And we get this is known to be also the minimax rate of estimation. And the main thing here is that we got rid of the size requirement. So if you now want to use the most natural basis, which is polynomial series estimator, you will again have this guarantee. But of course, this is all fiction because I don't know what beta m is. All right, but you first have to do this before you can do anything more adaptive.
Just
Yes.
one thing. So mu is what measure is mu? Or like what?
In this case, it's Lebesgue. Everything is Lebesgue measurable.
So
Thank you for that. I should have mentioned it.
So this basically says that if your basis function is a good approximation which satisfies this case like this, then the FW would get
This estimator,
this estimator would get that that rate.
will get that rate.
Right.
And this rate is the lower bound.
It is also a lower bound.
So this is minimax.
Instead, if you were just using the
Least squares,
square,
you will
then
not get
you will
this.
not get that, you get whatever you should. 1980s.
Well, not even that,
Not even-
not even that, because you will get that result provided the function is sufficiently smooth.
I see.
If the function,
Oh, okay, so there is.
in high dimension, you will never get this rate. So this is a regularization that says you can get this rate regardless of your choice of basis function. That's the, I'm glad you're slowing me down. That's the real, that was the gap.
Okay.
Yes.
So the rate at which the approximation improves, like the approximation theoretic property improves is important, right? In the sense that like, if you had like a weaker rate on the first line, you wouldn't be able to take k off higher and then still get the optimal statistical rate, right?
Sorry, say that again.
So like, you have this k to the minus 2 beta m over d rate
Yeah.
that you require approximation theoretically. But if you had something worse on the approximation side, you wouldn't be able to then take k off to be higher and then regress and get the right statistical rate.
You might be able to do it provided beta is large enough. So you might be able, if you have something that doesn't have a good approximation error, you can do what people call undersmoothing. You can increase the number of k because k up will not be enough. Increase your number of k, but if beta m is not sufficiently large, you will never be able to attain this rate. This is why this is sort of this is a necessary condition for this rate to hold regardless of what beta m and d is. Does that make sense? But this rate may be attainable for some value of beta m, even if your regression is not approximation optimal. It's not a good approximation. You just have to grow up how many basis functions you use, which makes sense. It doesn't approximate the function as well for a given k, so I need to use more of them to get closer. But that will increase the variance, and so there's going to be a trade-off. And at some point, the variance is going to be so large that you will no longer be able to attain this rate. So we consider this to be a necessary condition for that reason. And also, it's not a very restrictive requirement. Virtually all basis functions that I know of that I use in practice satisfy this property. Otherwise, we won't use them. So it's quite broadly, people who do approximation theory, this is something they're really concerned about. So we know a lot about this stuff. Is the statistical part, how do you, that I think, what at least we engage mostly with, not the approximation part. Okay. So maybe a few comments. So what it establishes, just to go back and look at the big picture, it establishes that the Forster-Warmuth learner is minimax with optimal with respect to the mean squared error for any basis system. And this is, we're trying to be a little more rigorous in terms of talking about the approximation. So these basis systems are known to constitute a full approximation set in the sense of originally introduced by Lorentz in '66, and Yang and Barron, who made it more accessible to a statistical audience in '99. And this includes polynomial basis for all combinations of beta m and d. The corrections that we introduce, A through C, in the Forster-Warmuth learner are key to get this result. And they obviate the need to control the size of the basis function and to worry about controlling that P transpose inverse matrix. Note also that A through C become negligible in large sample, and the Forster-Warmuth actually behaves quite similarly to the least squares in very large samples. And so this is a finite sample correction that gets you the minimax rate of estimation. Okay, so this is, I think, the only thing I'm going to say about adaptation. So one important property of the Forster-Warmuth learner is that it's actually bounded. Okay, the estimator itself satisfies this boundedness property, provided y is bounded in the second moment, there's a y is bounded. So what it means is, I'm going to step back a little bit. So there's this large literature on understanding the theoretical properties of cross-validation. And people have shown that if you do cross-validation, so this is all about adaptation. I don't know how to, so I have this, just slow down a little bit. We have this theoretical K out that you should choose. It depends on D and beta M. We know D, obviously, and we're assuming we know D at least. But you may also want to adapt to D, because the intrinsic dimension may be lower. And certainly you don't know beta M. So this is useless for practice. How do I pick K? So what we say actually is, we're going to leverage the theory on parse validation. And what's important in this theory is that you've shown that if I give you a collection of not just for any given learner, so I use wavelets, I use polynomials, I use splines, I use RKHS, I use neural nets. I have a dictionaries of learners, and each of them have bandwidth. So I do like a cross table, learner and bandwidth, and I get a large collection of estimators, M hats. Okay? Forster-Warmuth M hat. And I want to choose one. Well, what the theory says to do is, ideally, you want to behave like an oracle. What would an oracle say? What the oracle would say is, well, you give me all these estimators, and I know how to actually compute the mean squared error because I'm an oracle. So I can compute the actual mean squared error, and I can tell you for your sample size and your data which of these learners you should choose. Okay, so what they've shown is that if the learner is minimax optimal for a fixed bandwidth, for a fixed beta M and D, this is not our work, this is their work. Okay? And I'm an oracle, I can actually tell you which of those learners to choose. But if I'm not an oracle, I can use cross-validation. And cross-validation works because it's near oracle optimal. It's going to give you the mean, it's going to give you the mean squared error that the oracle would posit up to a little OP 1 over, and actually the rate can be 1 over n. So it's super close. Okay? And so, in other words, cross-validation adapts. It's a very general result. The main requirement, if you look at the proofs, particularly it's very clear in the van der Waals result, is that the estimator itself has to be bounded. Okay? And by virtue of this estimator, its construction needs it to be bounded. And so the selection problem is completely solved. We don't have to do anything by just leveraging this property of the learning. Yes.
Can you do this with fixed design, or do you really?
This is random design. Everything I'm saying is I, D, X, Y. Fixed design, I'm not sure. I'm honest, that's my honest answer. I'm not sure if all of this translates. The cross-validation results that I'm referring to is also for ID design. Both X and Y are random. There are some subtleties that come up sometimes with fixed design, and we haven't really thought about it. We haven't really thought to you completely stabilized me with your question. I nearly dropped my computer. We haven't really thought about fixed design. It's a really excellent question. And I honestly don't know the answer. So let me maybe stop here. I think I'm about a third into I was a little ambitious as to how much I would be able to cover. I'll maybe spend a minute just telling you what was next and what I didn't really cover. So what I didn't really cover is, and maybe I'll give you the motivating example and I'll stop there. Unless there are more questions, I can also stop here. More than happy to discuss. So my own work, I'm at the intersection of theory and practice. So I work in public health and medicine, and many of our applications are motivated by things like this. So I'll go straight to the examples. So we're interested in studies that sometimes I describe as semi-supervised learning, where we want to learn. I work with doctors in clinics, and they want to learn when they see their patients for routine visits, how can they predict the risk for diabetes without doing it really expensive and testing or invasive testing. All right. And so in this particular study that Cornelis, a former colleague of mine, they aim to develop a genetic risk prediction score, right? So there are a lot of genes that have been known to predict associated with the risk of diabetes. And the way they do this is basically they need a really good outcome. They need diabetes to be validated outcome. It can't just be looking at the data and you think that person has diabetes. They actually convene a panel of physicians. They do all the tests, measure all the biomarkers they need, and then they present it to the doctors, and there's a consensus diagnosis. Yes, this person has early stage diabetes or advanced diabetes or whatnot. Thank you, Demetrius. And so that's an expensive procedure. Doctors are expensive to convene a panel of 6 doctors. So you can't do this. This is like hundreds and thousands of people in the data set. You do it for at most a few hundred people. So you have very little labeled data and a lot of unlabeled data. A rich unlabeled data, a lot of covariates. And so the idea is you want to design the study in such a way that you leverage the labeled data to get a really good prediction in unlabeled data. Okay, so this is what we call counterfactual learning. What would have been the outcome for these individuals who have unlabeled data had we actually managed to measure their label? Contrary to fact, thus counterfactual. Causal inference is all about counterfactual things. So missing data is actually a counterfactual problem. It's a causal inference problem. What would happen if I prevented the missing data to happen? What would I observe? So that's one example. And then maybe in closing, I'll mention a second example. And then I'll stop there. So this example is an HIV example. As was mentioned earlier in the introduction, I do quite a bit of HIV work in Africa. And this is a study where we went to household. We did household visits and we had presented a survey. It's a general broad health survey. And then so we run through the survey. Most of it is uncontroversial. We just ask about the household, who lives there, how often are they there, what do they eat, how do they work, what are their habits. Okay, so people engage. And at the end, we ask, would you mind giving some blood? And by the way, we would like to do an HIV test. And we wait to the end because we don't want to start with that. And this is a very hard problem because the design is very simple. You just go to people's household, right? But it's very important to be careful how you design the study. The person you send to the household, for instance, this is in Zambia, we did it in Botswana and South Africa. If it's a young woman, if she's asking older men, the older man will feel like he's being disrespected. Why do you want my blood? What do you want to know about my HIV? I'm not going to give it. Missing data. Likewise, if it's the young man and the older woman will be very offended. Why do you want to know about my sexual behavior and my HIV status? No, I'm not going to give blood. Okay? And so these interactions matter. And you end up having a lot of missing data. We have, like, you can have up to 30% missing data. This is a real problem because, at least historically, I don't know if that's going to be true anymore with the new administration in the office, but historically, UNAIDS and WHO will use these types of studies to gauge how much HIV is in a region and then decide how much money to give to that region for HIV control. So if you have 30% missing data, we can show that in some areas, if you use the observed sample, you estimate 12% HIV in Zambia. If you just do the rough bound, that is, you assume everyone who is missing is HIV positive, or everyone who is missing is HIV negative, the truth is somewhere in between, you go from 5% to 35%. And 12% is what you have the point estimate. There's no way you're right. Because these missing data are not random. So this is again another kind of factual problem where we now want to predict the person's HIV status, given that we have all the other questionnaires answered. We have a rich set of covariates. And want to predict it where, contrary to fact, where we had been able to convince them to donate blood. Okay? And what we show, and unfortunately, I'm out of time. We just show you can modify the Forster-Warmuth to address both kinds of problems. I'm going to stop here. Thank you so much for your attention and for sticking around a little longer.
It's very interesting. Do you have a model for the missing, not at random? Because I see a lot of different missing.
We have a very clever model. Okay. I wish I thought of it myself, but actually I didn't think of it. Someone else did. So what we control in the study is the interviewers. because we hired them. So we have their CV, so we know how many years of experience they have. We know their sex, we know their age, we know everything we need to know about them. And as I said, if you look at the non-response rate per interviewer, it's actually highly correlated with all those factors. So obviously, the people who are more experienced have lower missingness rate. So this is not the interviewees, this is the interviewer, the people you work with. So we have like 30 interviewers. We got their CVs, we compiled the data. So why am I telling you this? Because you actually get a design-based solution. Because if you think about it, we send out these interviewers at random. The interviewer's characteristic is highly predictive of missing data. But the interview characteristic is completely independent of HIV status. There's no reason why a given interviewer will mean that a person they talk to has higher HIV or lower HIV risk. So interviewer characteristic is a random variable that's highly predictive of missingness, but completely exogenous to HIV status. And it turns out that that builds up an independence. This is what we call an instrumental variable. That makes interviewer characteristic an instrumental variable. And you can actually both detect the magnitude of the missingness of the random and you can correct for it. And it's remarkable because you actually get a correction. In this case, we get a correction that gives us a bound between 22 and 25% of HIV instead of 12%. And the only assumption that you make are actually assumptions that you control. They're design-based assumptions. You know that the interviewers cannot be correlated to HIV status in the population. And you know that the interviewer characteristic is highly correlated with missingness. And you can use that to back out the magnitude of the bias. And we have a couple of papers where we actually use this, and I'm happy to share them if it's of interest. So these are kind of solutions they come from the causal inference literature, where we move away from assuming things are happening at random and try to find other ways of getting a sense of uncertainty. Thank you. All right, I'm going to stop there. Thank you so much.
I know there have been a lot of introductions. It's a great talk.
Thank you.
And but if you have any remaining questions, you can speak to us. Maybe we'll be able to get you head out for lunch.
Do you know how to do more complicated spaces like Bessel spaces?
Yeah, you can the best of spaces. So let me qualify that a little bit. Adaptation in Bessel space is more complicated than the kind of things that we're doing. So the right answer is I think it's possible, but we haven't done.
I've been working on that.
Oh, okay. In what context though?
Like just univariate regression over like total variation spaces, choosing an adaptive bandwidth.
Okay. All right, cool. Yeah, no, we should talk more. That's I think that's actually very important in many areas because if you don't do that, you're assuming everything has equal smoothness everywhere, which is ridiculous.
Yeah, so we also did a like kind of reduction in bound memory for non-selection response.
Do you have a paper already, or?
It's just I just submitted it. Yeah.
Ah, okay. Is it on the archive as well?
I haven't looked at it yet.
Let me know when you share. I would love to do that.
Is there any connection to abstentions with the
To what?
abstention? So you say I will predict on this instance, like if it's too far away from the support of my data. Can the Forster-Warmuth predictor can think of it as abstaining on certain?
Oh, abstention. Let's see what you're asking. I think you can. So. I think maybe the way I would think about it is maybe thinking of it that way would allow you to say something more about the space where we're not going to predict. We're basically just throwing it out. And we can do that because our metric for how good of a fit averages over the support. But if you wanted to restrict the averaging over a support where you have very limited data, I think you would need to do something different. We're not going to do well. So in other words, I think thinking of it that way may be helpful in resolving a limitation of our approach. because it would allow you to learn about how badly you're actually doing in those areas where you're not getting to learn. So, you know,
And what about the connection to like the missing, not at random stuff?
yeah, so the missing on at random stuff is, basically what's happening. So I understand your question. There's still an assumption that, for any value of X, you at least have some label data in your training set. Which is a bit different. So the missingness at random, it just, relaxing missingness at random just says that, the missingness process and depend on why. But it doesn't say that you don't have any label data where X is. So we still make that strong assumption. We refer to it as positivity. Some people refer to it as overlap. That you do have some label data for all values of X. So it's somewhere in between. I don't know if that's.
So somehow having, say, two different types of interviewers, or like the same type of individual help to
Helps you, exactly. Which is actually a strong assumption, because not all interviewees will react the same to all interviewers. So there's an assumption that there's at least one interviewer who will be able to get every person to respond, which may not be true. Maybe some people. So in that case, we don't get identification, but you can construct bounds. Let's say things are stopping between these values and those values. That's all you can verify. Actually, that's a good point, because I think even the Forster-Warmuth, you might be able to extend it to allow for bounds, which we haven't done. That may be the most agnostic thing that we should do in those areas. There's very little, at least in the statistics literature has shied away from this issue. And I think it's because statisticians just think if you don't have data, you should talk about it. As opposed to saying, well, you can still produce meaningful bounds, or you might be able to think about a trade-off between relying more on the priors in areas where you don't have data. But we're not very apt at doing that. So that's a really good question. I'm curious. I was quite nervous coming in here because I'm not used to speaking to folks who are more heavily computer science folks. Can you tell me a little bit about your background? I should have started with that. Are you all computer scientists? There's some data scientists? Oh, okay, okay, all right, all right. Okay.
Folks over here, they just sit here because I went.
Oh. Well, thank you.